That's how I ended up here today. Done. Yeah. Okay, so could you enable screen sharing? I just need to be able to share the screen. So are you the host? Is Professor Beaucage the host? Otherwise, you're just going to get like occasional glimpses of me when I'm over here, and most of the time I'll be over here.
Yeah, he said it doesn't need to be recorded.
Well, it's being recorded, I guess, but it's not going to have the slides shared. So unless I can share the screen, I can't do that. Yeah. So I need you to, if you're the host of the talk, I need to be enabled. There we go. All right. I can share this. All right. So in your Zoom, are you seeing the talk or the are we seeing the talk or the are we seeing the talk or are we seeing
Is the screen up in the Zoom? Yeah. Okay.
all right. Well, then with all of that out of the way, let's get going. Okay, the objective here is to give a quick overview of what inelastic scattering is for in the context of polymer dynamics, and then hopefully to talk through a little bit of maybe what I've done and how I've used it, but mostly then to turn to the papers you were given. Has anybody read those papers that you were given yet? You just put them up this morning. Okay, well that's unfortunate for me. So I read those papers, and the thinking I had was after we go through the basics and do questions, we could start talking about what those are. There's some interesting details in that that maybe will help you understand what they're talking about. So with that said, these techniques are a big deal. So they gave a Nobel Prize to Shell and Brockhaus in '94 to honor or recognize the importance of neutron diffraction and neutron spectroscopy. And so the quote here, so both methods are based on neutrons flowing out of a neutron reactor, nuclear reactor, which is not the case anymore necessarily. When neutrons bounce against or are scattered by atoms, the sample being, the sample of the atoms in the sample being investigated, their directions change depending on the atoms' relative positions. This shows that the atoms are arranged, how the atoms are arranged in relation to each other. That is the structure of the sample. Changes in the neutron velocity, however, give us information about the atoms' movements, i.e. example being their individual or collective oscillations. That is the dynamics. And so there are two different flavors of neutron scattering that are recognized here. So in the context of why this matters to a polymer physics class, there are many different types of relaxations that are happening in your polymer systems. And there's a broad range of techniques that cover different time and length scales. So take a second and just like absorb the magnitude of the chart here, because it's a very busy chart. But the notion being that you go through a range of time scales. You go through a range of length scales when you're trying to understand a material. Okay, so you might want to understand, polymers and proteins that are, moving on this length scale of, what are we saying here? Nanometers to micrometers, angstroms, that time and length scale. And then time, being nanoseconds to picoseconds, microseconds. And so slow to fast dynamics, big structures to small structures. Okay, so depending on what particular piece of that you're looking at, what type of property of the polymer you care about, what element of its structure, you're going to use different methodologies to study this. And so you can see some more benchtop or other types of techniques such as NMR or dielectric spectroscopy, infrared spectroscopy, light scattering of various flavors. They're missing some of these key windows where you care about the polymer dynamics. And that's why you end up needing to use neutron scattering techniques such as spin echo, backscattering, or time of flight spectroscopies. They sort of sit down right in the middle of this, and I've told you guys have covered X-ray PCS before. So what's the big problems with X-ray PCS? Did we go over why it's a terrible idea? How you're cooking the sample?
Yeah, it's,
Destroying it?
you don't want to do it to anything like soft, or not soft per se, but
Anything that has
destroyed.
anything that has susceptible chemical bonds is going to be destroyed simultaneous to being measured. So it's sort of a moving target. And benefits of neutrons are that they're highly penetrating and they're non-destructive. So neutrons will give you some amount of activation, but in general, you're not destroying the sample. You might be destroying a few atoms, right, in your sample by having a neutron fuse on and creating an isotope or something and then having that decay. But that's not generally a destructive method. So you can measure systems that are susceptible to damage, X-ray damage. The other big advantage with neutrons that we'll go over is contrast. So we've talked about neutron scattering for small angle before, SANS. So we did talk about SANS and the idea of neutron contrast matching and manipulation. Yes. Yes. Cross sections changing, things like that. Okay. So the notion there is that you can emphasize particular parts of your system. So if you want to see the dynamics of one part, not another, there are sometimes in techniques like spin echo where you can emphasize one part of your system over another. And I think that's even part of one of your papers for this week. Okay, so the notion of the other big thing to take away from this is you see how these are not, so your structural techniques are sort of a single bar, right? So SANS or reflectometry or diffraction, time-based dynamics techniques like vibrational techniques like infrared or X-ray, infrared light spectroscopy, IR, Raman, Brilliant. These are single lines in time or single lines in space. When you're doing these neutron techniques, and a bit in the X-ray PCS too, we'll acknowledge, but you're covering an area, right? A rectangle here, which means you're simultaneously probing time and space in the system. So I'm asking the question, how does something move over a certain distance? Or how does a structure of a certain size change as a function of time, right? So there's a coupling between the length scale and time scale. So you're not thinking about these things as a single spectrum, but as a summation of multiple spectra, each one probing a unique length scale. Okay, so you're really bringing together not a 2-point correlation function, how do I change in time, but a 4-point correlation function of where do I go in time and over how long did that take to get there? Or if I'm a structure of this size and I change to this size, how did the system change? 4 points, 2 points in space at 2 different times. So it's fundamentally a 4-point correlation function. Okay, so scattering methods, elastic scattering, inelastic scattering. So SANS, SAS, elastic scattering. What happens when you have an event? You have a particle coming in, we're going to call them neutrons today. So you have monochromatic neutrons coming into your system. Okay, you've scrubbed the spectrum down, you have a single wavelength coming at you. It hits your particle, it scatters off at a different, or your sample, excuse me, scatters off at a certain solid angle, and you have your incident energy, your incident wave vector, your outgoing wave vector, and your scattering wave vector is created by that collision, right? And the scattering wave vector then is related back to real space through Bragg's law. Okay? Remember Bragg's law? Somebody gonna write it for us? Yeah, okay. So it's 2 pi over q, right? So or 2D is a D equals D, yeah. So, wavelength dependence, great, incident, like output, and your scattering wave vector. Good. Now, what happens if the magnitude of that scattering wave vector is not the same in the outgoing neutron? Right, so your incoming neutron has a certain scattering wave vector. Probably we should call this the incoming. Your outgoing then has got some change in its magnitude. It has changed velocity. So we're talking about the momentum being changed. So my incoming neutron had one energy, hit that coffee cup, some water molecule or polymer or something in that coffee cup was fluctuating. It has some natural fluctuation rate, right? It's viscous liquid. It's moving around with thermal energies. And in the course of their collision, it got a little kick, right? So it's like a rolling pool ball. You hit it with the cue ball, and if the pool ball's rolling away from you, you lose a little energy in the cue ball and it scatters away more slowly. If it's coming towards you, maybe you get a little energy and it scatters away more quickly. Okay? That's what's happening in the collisions for inelastic scattering. So what ends up happening is your scattering wave vector has a momentum transfer component in it. Okay? That's fundamentally what this is. So if you have a lot of energy transferred, fast motion, you see it with a big change in velocity. If you have a slow motion, you have a small energy transfer, and you see it with a small change in velocity. And it's the magnitude of that change in velocity that leads to all the different flavors of spectrometers that we design, etc. Okay. Before I talk about this, we should also talk about in that quote at the beginning. So they were talking about nuclear reactor. So traditionally, neutron techniques are you poke a hole in it, and then you have that streaming out. You put a little box of really chilled out water or hydrogen gas or something that's been liquefied, and you put it there and you moderate the temperature of the neutron. Right? So the neutrons are streaming out. They have a certain energy. They have a certain velocity. That's a temperature. And so what happens is through multiple collisions, they thermalize, and then you get a certain wavelength band that comes out of that moderator. Okay? This is moderating neutrons. The same thing you do when you're running a reactor, changing the energy of the neutron. And then you're going to have that neutron streaming out. It has some bandwidth. You're going to then use like a spinning tube or something that will velocity select. So the velocities of thermal and cold neutrons are thousands of meters per second. So these are things that we can mechanically capture, right? So if I want to use a very defined monochromatic source from a reactor that's continuously streaming neutrons, I'll put like a corkscrew in the pack. And that corkscrew will absorb anything that's going too fast or too slow. And as the corkscrew turns, right, there will be a spot where that neutron can just slip through. And if it goes too fast, it'll run into the front of the corkscrew. And if it runs too slow, it'll run into the back of it and be absorbed. Right? So you can get this single wavelength out of that. And that's how a reactor, you can generate roughly monochromatic neutrons. If you want to be more specific, you'll use a crystal that has a reflection that's at a single wavelength. And we'll talk about that in a second for triple axis. But you can velocity select, and then you can use a crystal to even more tightly refine that bandwidth. Okay. Has anybody heard of the new way we do neutrons? We don't use reactors. Well, I mean, we still use reactors, and you need to use reactors. They're very good for scattering techniques, but there's another method that's all the modern neutron sources are being built on. It's called spallation source. Okay. All right. So spallation sources are based on proton accelerator, right? So you just create a normal linear, like a linear accelerator and accumulation ring, and you accelerate your protons using radio frequency or something, and you get these near relativistic protons, and then slam into a mercury or tungsten or some other heavy target. And that will destabilize those nuclei, and they will go splat, right? Spallation. And as they decay or as they break, you will have neutrons released. And the beauty of this is not that you don't have a terribly radioactive situation going on. Of course you do. You're destroying nuclei, you're breaking apart, you're generating neutrons. But when you turn the proton accelerator off, that process stops cold. There's no ongoing issue. There's no nuclear fuel. It's just on or off, okay? And that's in the target source. You're never changing, I mean, you are changing it, but very infrequently you're changing those. And so that's what they've started doing now for all, not all, but most new construction. So the facility at Oak Ridge National Lab in the US has a spallation source. It also has a reactor. The spallation source was built in the late 90s. There's a spallation source in the UK, called ISIS, which was very, very, not great, not great. It has an Egyptian theme, so like that's fine. They had an Egyptian theme at the time. So that was really the first major spallation source. Then the current other sources at NIST, there's a reactor that's not really running. There's a reactor in Germany and Munich that's not really running. There's a major reactor in Grenoble that's running, and that's a good source. They're building, the European community is building a spallation source in Lund in Sweden. That should come online sometime soon. The Chinese spallation source is being built down in Guangzhou, so outside of Canton. Well, I guess it would be called Canton in the past. And then Oak Ridge is trying desperately to get a second spallation source built, which would have different wavelength characteristics. Yeah.
Have you been to any of them besides the Oak Ridge one?
Yeah. So I've been to the UK, I've been to Lund, I've been to Grenoble.
And you did research at all those places?
I did research in Grenoble.
Oh, cool.
No, and I've also been to NIST. I flirted with a job in the UK and France in the past. Didn't do that, obviously. So, yeah. Okay, so any other questions? So spallation sources are the way that's done now.
So are those like, he was talking about for the X-ray diffraction that you just, when you use that down at the Oak Ridge universities, you can just do, the Oak Ridge site, you can just do a lot of samples right in a row, like very
So
quickly.
X-rays.
Can you do that with the,
Neutrons, the flux is very different.
okay,
And that's an important point. With neutrons, you know, they're precious. That's the nice way to say it. Is that the flux is low by orders and orders of magnitude. So an experiment that might take a synchrotron, you know, you might overcount by flashing your sample for 1/4 of a second or 1/10 of a second. That experiment might take you 2 hours at SANS. And so you're the notion of when you use neutrons versus when you use X-rays, you really need, you should really be needing to use contrast or needing to do penetration, like deeper penetration in your sample, or you need to do dynamics, is when you would go to neutrons. Otherwise, X-rays are much faster, very clean information. But again, if it's light elements, you don't have the contrast. And so I'll show you a figure that sort of crystallizes that point. So X-rays scatter from what?
they're very small, I don't.
X-rays scatter from the electron density around an atom, okay? So basically the X-ray scattering cross-section scales with the atomic number. So metal scatters, bone has calcium, calcium's not that heavy, right? But it has sufficient atomic number to see differences from carbon, nitrogen, oxygen, hydrogen. Neutrons, you see hydrogen real. And so those light elements are why you care about this. And that's why polymers and neutrons are like really good friends. Biological materials as well. The other important thing I meant to mention about spallation sources. Spallation sources are not continuous. They're pulsed. Okay. So whereas a nuclear reactor, once it's going, is going. And you're just streaming it off, right? It's just a continuous stream. A spallation source, because you have a proton, like an accelerator, it's getting neutron, or these protons are coming off, and they're coming off in packets. Okay, and so Oak Ridge, the spallation source at Oak Ridge that I know so well, is a 60 hertz pulse. The proposed new one is 15 hertz. The one in Europe, I think, is 20 hertz or 17 hertz. That's some goofy thing because they have a So anyway, it's like 20 hertz or something. And so the notion being you get a bright pulse at the source, so at the center, you get all these neutrons generated all at once with all these different wavelengths every time it gets hit. Okay, so you hit the target, spallation happens, and you get all these neutrons, and they're running out from a central point, and the spectrometers and things will be arranged around them, and they'll be running out. There's beautiful things you can do with that when it comes to dynamics, because what you care about in dynamics are getting these little packets of monochromatic neutrons, generally. There are ways around this, you sacrifice and do things, but generally you want these little packets that are focused in time and intensity. And when they hit your sample, you can see the spread of that intensity tells you that something has changed its velocity. So it goes through your sample, and it goes from being this nice delta function to some broad Gaussian function. You know that the distribution in energies, or distribution in times at which your neutron arrived at the target, or the detector, excuse me, that reflects changes in momentum in the neutrons that are coming from their interaction with your sample. That's dynamics. Okay, that's why the spallation sources are so good for that. At a reactor source, you're making compromises to get there. Now, in spallation sources, there are really different ways to do this, and we don't have to go into all those details, but that's the point. So we care about time because we see changes in momentum. That change in momentum is actually a physical change in the velocity of the neutron. All right, so okay, coherent versus incoherent scattering. So when you think about structural measurements, SACs or SANs, what you're seeing is coherent scattering. It is coherent, okay? So this is constructed wave functions. Coherent, when you hear it, it just means collective motion in the context of dynamics. It means two things are a certain distance apart from each other, and we're asking, does that relative distance to each other, does that change as a function of time? So if I have a structure and it's got some signal because it's the Fourier transform of the pair distribution function, okay, if that changes in time, I might see that change with a spin echo technique. Generally, with the in backscattering and simple inelastic measurements, we're more interested in seeing coherent or incoherent scattering. And incoherent scattering you can interpret as self-motion. So if I see a proton in water and I'm doing a backscattering experiment, the dynamics I'm observing are generally, not entirely, but majority of what I'm observing are translation and rotation of that water molecule. So it's moving itself, and you're seeing the protons in that water moving as a function of time. And then the wave vector is telling you how far did they move. So you can think of it as an incoherent scattering experiment. What you get is you start off at position 0, 0, 0, and if you move, the scattering will reflect that. You'll go from an elastic scattering signal to an inelastic scattering signal. And the distance dependence of that is how long does it take me to move out of a sphere of this size? Okay, that's one scattering wave vector. And the average time it takes me to get out of that will be reflected in the spectrum at that scattering wave vector. But if I make the sphere bigger, how long does it take me to get out of this sphere? Well, then that's another scattering wave vector, and the spectrum is going to reflect that. Okay? And so on and so forth. Whereas a coherent, the dynamics experiment for a coherent signal, which you might see in spin echo, is really saying, all right, so we're two adjacent polymer chains. We have a nice SAN signal from this correlation we have, and let's wait 30 seconds. All right, now let's measure that same Q vector. And on average, I've moved away to a certain percentage of the time. And so you'll see simply a decay in the structure that you're getting because our relationship has changed over that period on average, right? So these are all ensemble methods. All right, so self versus paired. Okay, so this is just I've said most of this stuff already, but this is talking about the scattering lengths for different elements. So whereas X-rays scatter from the electron density, right? They just, as atomic number goes up, the scattering length of that element goes up for an X-ray. neutrons are sensitive to the nuclear structure, okay? So these will vary somewhat between elements and not necessarily following the atomic number. They can be both positive or negative. So that's a thing. They can also vary by isotope, right? Because isotopes are a different number of neutrons in the nucleus. So different nuclear structures are going to interact differently with neutrons. On top of all this that you're seeing here, so all these different isotopes and elements have different scattering lengths. The wavelength of the incident neutron also affects the scattering length, right? So if you've ever studied nuclear reactor design, you know that you moderate the neutron to change the cross section of the other uranium pieces, right? So that's why you're running water through there, or you're running heavy water through there. So light water reactor, heavy water reactor. These are different absorption factors for the neutrons that come off of that fuel. So wavelength dependent, isotope dependent, element dependent neutrons, you can tune all these little knobs to get differences in the scatter. And the most relevant to us is hydrogen. So hydrogen, typically, what, like 99.7% or something of elemental hydrogen is a proton, right? So it's just a proton with an electron hanging out. That's it. That's hydrogen. But some small fraction of the time you get heavy hydrogen, like deuterium, which is a neutron and a proton and an electron hanging out. Tritium, we don't see a lot of it because it's just not very stable. It goes away quite quickly. So there's not there's a very interesting calculation, you should look it up, of like how much tritium is ever available on Earth at one time. It's like an astonishingly small number. You just wouldn't believe it, but it's always decaying away, so you can't really leverage it. Okay, so in the case of water, we look at the pair correlation function of water. So this is like, what are the relative lengths of these atoms in a set of water molecules? So each one of these correlations is going to give you structure. If you look at it in X-rays, you get one structure factor. This is just a simple diffraction measurement. And it's telling you, okay, you do the Fourier transform of this, and you end up getting Q versus distance, right? You just transform one to the other. And okay, you get basically the average distance between these things. With neutrons, you can do this experiment quite differently. You can do it with H2O, you can do it with D2O, you get very different signals. So a proton has very little coherent scattering, but an enormous amount of incoherent scattering. Whereas a deuterium atom will give you this very nice structure. You'll see the correlations, it's all there. And then with neutrons, the other interesting thing you can do, and I should have shown this as a, let's see if I can write on this. I don't know. Uh-oh. Let's go back. Well, back. How about that? Okay, so roughly when you see these spectrum for neutrons, this would be the change in energy. That's supposed to be a delta. And this would be intensity, okay? So you can have neutrons lose energy, you can have neutrons gain energy. It's fine. Structure, generally, all these structural spectrometers ignore inelastic scattering. They don't even acknowledge it happens. And so what they're essentially doing is integrating across the whole width. This is why this is multiple scattering, this is inelastic scattering, this is a signal that compromises your SANS measurement. If you do this exact same experiment on a spectrometer, what you can do is actually isolate the incoherent signal. So this would be zero energy change, right? So that's delta E equals 0. And so if you define how much energy transfer you're willing to take, you can see only the coherent inelastic scattering and ignore the incoherent or the inelastic. Whereas most structural spectrometers, most of these instruments they're designed to ignore it. And so the picture I drew here assumes a logarithmic scaling because we're just like that. And it lies, right? So in reality, a typical inelastic scattering experiment is more like this, right? Where your inelastic signal is tiny. It's like 99.9% of the scattered neutrons don't scatter inelastic. They're really not supposed, like, it just doesn't happen very often, but when it does, it's very informative. Okay, so yeah, this is the picture. I guess I thought ahead of that. This is what I was trying to explain. So in a neutron experiment, you're seeing a more complicated signal than you would in an X-ray experiment. So if this is scattered intensity, the total scattered intensity versus the different scattering wave vectors in Q, versus the energy transfer, which we call omega, but you can think about it as just delta E divided by Planck's constant. And so what you'll see is that, okay, you have some total signal here, the black line. There's an incoherent self-motion where you're seeing some energy transfer, and the shape of that varies widely as a function of scattering wave vectors. So different length scales, you see different kinds of physics, different kinds of motion happening at different length scales. So at long distances, you'll see just density fluctuations, and that's the speed of sound. Okay, so as you look at that, your energy transfer for these large peaks will be the speed of sound times Q. Right, so this is the first feature you would probably see. So if you have some polymer melt that you've solidified and you're going to use it for something and you want to know what the speed of sound in it is, well, you could do this with a brilliant instrument. You could do this with a microphone. But you also see it as density fluctuations, which are what sound waves are. So this is actually measuring that phonon through your material. As you go to shorter length scales, these incoherent broadenings in your peak are going to tell you about different types of motion in your system. So it might be backbone relaxations, right? Slow. You start slow. So maybe you have incoherent scattering coming from the relaxation of the polymer backbone. Or you have relaxations in the side chains. Or maybe you have a co-solvent in there to keep things plasticized, and you see the diffusion of the solvent. And as you look at these widths as a function of Q and as a function of time or a function of energy transfer, you can back out things like the diffusion coefficient. You can back out things like the viscosity of your polymer, right? So like a Rouse dynamic, you would see that very well with spin echo techniques. Okay. The amplitude of this central peak is the structure. It's the same thing that you're measuring in a diffraction experiment or a small angle experiment. That central line. Okay. So essentially what you're doing with neutron inelastic scattering techniques is you're taking that structure signal that you're getting from SANS or diffraction, and you're just expanding it into another dimension of time. Okay, any questions on this? Make sense to everybody? All right. So, yeah, so that brings us back to then this kind of question. So we have different windows of time for different types of broadening in your system. And so we've talked mostly about slow stuff like Rouse dynamics or chain fluctuations. You can also get sort of peaks out in the very fast dynamics. And those are going to be like molecular fluctuations and vibrations. So very much the same things you might see in a Raman experiment or an IR experiment. But sometimes you really need the neutrons to do that. And so this is not what we're going to talk about today, but neutrons are really powerful for things like magnetic moments. So when you're sampled, so anybody working on these Majorana quasi-particles, things like that, they're using neutrons. So that's one of the big things that neutrons are important for right now. Every time they put out a good neutron paper, like Apple or Microsoft comes and hires the person away from the lab, like it's repeatedly happening. So what else? Yeah. So the point here then is to say we have different energy transfer regimes that probe different types of dynamics. Those are going to require very different instrumentation and spectrometers. So when you go to do this type of experiment, you have to ask the question, which one of these techniques is right for me, is right for the question I'm asking of the system? And then do I need to combine these together to cover a broader window in time? So typically what you care about is some variable is going to be changing the relaxation time, right? Okay, I want my system to be less viscous. Which dynamical mode am I trying to modulate? So as you change that, you need to cover a range of times. And then the different length scales will have different times embedded in them. So let's start with, we'll have 4 techniques we kind of talk through in some detail. Not that much detail, but we'll start with the classic, the Brockhouse triple axis. Okay. So in this experiment, you're bringing in a monochromatic neutron beam. You're going to use some kind of an analyzer or a selector crystal there that is going to reflect off only a specific wavelength. There are some materials like silicon, if you cleave it on a certain axis, the 111 axis or the 001 axis, you can select a specific wavelength of neutron that will reflect off of that at a certain angle. All right, so you take that, you shoot it up towards your sample, and you run it through a monochromator, and now you have monochromatic neutrons coming at your sample. You then take that off the sample at a certain certain angle that you care about, right? So there's some wave vector you care about, and what you're going to do is you're going to spin this, right? So this is an arm. There's 2 arms, and so you're going to sort of change the angle to see the scattering wave vector change. And then you're going to have an analyzer crystal here at the end that is reflecting also a single wavelength. And what you'll do is you'll turn that, and then you'll take that to the detector. And what you do by changing both the angle of the analyzer crystal and the arm that defines the scattering wave vector Q, you can vary both Q and delta E or omega for a single point along your system. Okay, so you're measuring the change in intensity. Let's go back a slide. All right, so basically you pick a single value of Q, so like one of these slices that we're taking, and you measure a point at a time. Okay, and then you go back to the next Q and you measure a point at a time again. So this is a very laborious, very slow method where you're counting neutrons literally one at a time coming off this triple axis. All right. So yeah, so this is what it would actually end up looking like is you get your first reflection coming off the source. It's going to hit your sample. You're going to then move everything around with your detector analyzer system on the back end. Okay, so very slow, very laborious. Yeah.
From the diagram there, is the selector crystal that first like block box, or is that thing? Okay.
That's the monochromator. So you're selecting the incident energy with this one.
Gotcha.
And then this one here, 5, is going to be the analyzer crystal. And so that's only, the idea is that both of those have some selectivity based on the angle of exactly what wavelength is coming. So anything that's not matched up to that will pass off at an angle that's not detected.
Okay, cool. And the blue is the sample.
Blue would be the sample.
Excellent. Thank you.
Okay, so you can kind of see how this is not an optimized design, right? You're taking a point at a time and you want a spectrum, and you want a spectrum at every key value. Now, this is still used. There are multiple triple axis experiments out there. They're quite useful specifically for magnetic systems where you don't care, you care about fidelity of a very detailed portion of your system. You don't so much care about the whole spectrum. And so if you just want time to get on there and check your one little magnetic feature, very practical, very useful still. Much easier to get time on that instrument though. So as you know, as happens, time progresses, and they discovered that it's better to just measure the whole spectrum at once. So once they understood some of these concepts, you just build a big wall of detectors. All right, and what you do is you monochromatize your neutrons up front. You let them hit the sample, and then you clock it. So you measure when it hits, so you know what's coming in. You take these as little chopped pulses. Okay, so sorry, let's rephrase. Almost all of the time of flight instruments that are designed right now are they're time of flight based on choppers. And choppers means we are physically chopping that continuous neutron beam coming out of the reactor. So we're cutting it into little time slices at a certain intensity. So I say, okay, at time whatever, my continuous stream is coming in here, and then I have this series of choppers that creates little packets. And it creates packets with sufficient temporal resolution that you're not overlapping, and that you're cutting out the rest of the wavelengths. So it's kind of a complicated design to arrange your choppers correctly. Spallation sources are different, right? Because they just give you a pulse and a pulse and a pulse. So you don't need to use The choppers you use on a spallation source are different, and they sacrifice less signal than at a nuclear reactor. Okay, so the point being then you hit your sample, and because you're coming in at this narrow slice in your bandwidth, right? Hits the sample, scatters, changes energy, goes from if you're thinking about intensity as a function of time, so if this axis might be time, your sample gets hit with a nice block of neutrons, and then by the time it gets to the detector, it's spread out into some Gaussian function, right? And the shape of that is going to be related to the dynamics, right? So it's going at all these different angles, and it's also being spread in time, and that's exactly the kind of thing that you're seeing in a time-of-flight spectrometer. So this is a pretty good design. The issues that arise from this are actually just that you can't see dynamics that are slower than a certain value, about 50 picoseconds. Why? Because the change in momentum from a 2,000 meter per second neutron to a 2,100 meter per second neutron, as that number gets smaller and smaller and smaller, it's harder to clock it electronically. Okay, so what you're really seeing is the time it takes to get here versus the time a scattered neutron takes, which could be faster or slower. But this is an electronic clocking problem that you ultimately run into with the time-of-flight instrument. But it's beautiful. It gives you all kinds of information about just the tail end of slow motion, of slow, like diffusional relaxational motions. And then it gives you all of this vibrational data. So if you're doing hard condensed matter physics, this is the place for you. They built 4 of them at the spallation neutron source because it's just perfect. And you can't possibly get time there unless you want to write a beautiful paper about magnetic materials and superconductors. That's what they do. Polymer people were over here, where you get a lot less credit for things. So, okay, so to solve the timing problem, they created what's known as the backscattering spectrometer design. The backscattering spectrometers are all based on the use of one of those analyzer crystals. And so there's a fundamental difference between a reactor-based backscattering instrument and a spallation-based backscattering instrument. This is showing you the design of a reactor-based instrument. And the notion here being your neutrons come in, continuous stream, roughly one wavelength. You hit your sample, it scatters at a defined angle, and then it hits what's called the Doppler. And that Doppler is a reflector crystal that selects only one wavelength. Okay, so you're coming in with this broad band of different neutrons. And what you're expecting to see at the detector is that same broad band of neutrons and the same intensity from the scattering. But this reflector crystal only reflects one wavelength. So basically what it's telling us is if I put a detector that's only taking the neutrons from this reflector crystal, it's saying, well, whatever came in at whatever time that came in, if it comes off the sample and hits my analyzer crystal, then it must have changed energy to be at that energy. And then you can just sort of do the math and back out what's the difference in spectrum due to the reflection, right? So you're measuring that at a specific location. And you do this for a number of different positions. And what you do is you move this back and forth to vary the scattering wave vector. And what it does is it takes the velocity encoding out of a physical clocking, and it puts the velocity encoding in the wavelength that's reflected. So only the wavelengths that are reflected are what you see in your signal. And that's a way of just cheating the clock, right? Because it doesn't matter what you see, it's okay, you still have a clock. What the resolution isn't that electronic clocking, it's the reflections off this crystal giving you a new spectrum in time. All right, in the spallation version of this, you don't have a single Doppler moving back and forth. You have an array of crystals around everything. And you're taking the white beam coming, well, not a white beam, but you're taking a broad band coming in. And then you have an array of detectors. Yeah.
Doesn't that run into the same, or like, that it's very time consuming?
It is not a fast experiment, but it's not, this is not a terrible experiment. So all of these are These are spectroscopic techniques now. So you're seeing a broader band, you're measuring, in the case of these backscattering instruments are slow, they're not terrible. The new instruments at spallation sources are pretty fast. They're basically like a time of flight instrument, because they have an array of analyzer crystals, and then they have an array of detectors as well. All right. Then the cool one for polymers. So you still run into timing issues. And so with backscattering, you can get down to something like nanoseconds. So you can go from time of flights, you're seeing motions from femtoseconds all the way up to 50 picoseconds. With a backscattering instrument, you might go from 10 picoseconds up to a nanosecond, maybe 3. They'll lie and tell you it's 10. It's really 3 or 1. So those ranges. If you want to go to slower dynamics, you need this neutron spin echo technique, and that's going to take you from picoseconds all the way out to hundreds of nanoseconds, which is really where polymer relaxations are. That's the meat of that kind of dynamics experiment. They special design ones trying to get to a microsecond. No, they did it once. It took them like a week to do it. It's not practical. The best, newest ones, you're talking about hundreds of nanoseconds regularly. So these are relaxational motions in the polymer chain that are occurring over hundreds of nanoseconds. Okay. So how do we encode neutron velocity in a different way? The idea is to manipulate the precession, the spin of the neutron. And so what you do is your neutrons enter the system, and we think about neutrons have a precession, a spin. So if you polarize your neutron, and then you pass it through a defined magnetic field, you can define the rate of precession. So this is like an NMR experiment. So essentially what we're doing is we're putting 2 gigantic NMR coils back to back. So the first coil is defining the magnetic field, very homogeneous magnetic field. Polarize your neutrons, you allow them to precess. They're passing through at a defined velocity now, right? They hit your sample. They're spin flipped, fine, and then they hit the sample. They are scattered or don't scatter or whatever they do in the sample. Okay, so the neutron hits your sample and it can speed up, slow down, or stay the same velocity for a given scattering wave vector. And then on the back end, after you go through the sample, well, what you're doing, you have an entire second NMR coil on the back, and you swing it around for defining the scattering wave vector, and then you impose the opposite magnetic field, precisely opposite magnetic field, and so the neutron will precess in the reverse direction. And when it gets to the analyzer at the back, if the neutrons haven't repolarized, because what you're doing is you're creating an echo of the initial polarization. So I polarize at the start, move through at the defined velocity, precessing. If I didn't do anything, I just passed straight through, didn't interact with the sample, I precess back exactly the opposite, and spontaneously everybody will polarize at the analyzer. And the neutron will pass through the analyzer, and I'll see the same signal. I'll see 1. If I change velocity, I don't spend enough time, or I spend too much time in the opposite magnetic field. And so I don't come back together at polarization, and I get rejected at the analyzer. And so my signal is not 1 anymore. It's 0.9 or 0, depending on what fraction of my neutrons passing through have not repolarized. And so what this is telling you is that initial structure I created is gone or not. And this tends to be at longer wavelengths, so colder neutrons, and it's useful for slower times.
How do you tell the difference between it slowing down versus speeding
You
up?
don't.
Okay.
You don't. And in fact, you don't think about that for any of these techniques. Slowing down and speeding up, you don't worry about it because it's just where did you hit the motion?
Okay.
All you really can tell is the time scale of that motion, whether you gained energy from a motion or you lost energy from a motion, it's the same motion. So it's like, did I hit the pool ball from behind or that was moving already, or did I hit it from the front? One case, you're going to sort of give momentum. The other case, you're going to gain momentum. So it's a gain side, a loss side. And the peculiarity of that is in spin echo, it's just up or down. But you can gain as much momentum as you ever could want. So on one side of your spectrum, it can go to infinity, essentially. On the loss side, though, I can only lose as much momentum from my incoming neutron as I have. So if it goes to a dead stop, that's as far as I get. So actually the spectra, when I think I have, do you have a spectrum like this is what like a time of flight instrument might look like. This axis might go on forever, right? Until you start overlapping your next band. To the gain side on the top, you can only gain as much energy or lose, I'm sorry, the loss side is up. And so you can only lose as much energy as you had. Right, so my guess would be that experiment was conducted with 1.8 angstrom neutrons, because that's how much energy you get from 1 MeV neutron site. That's as much as you have to get. That makes sense. Sorry, let me go back. Other questions? Yeah.
What type of motion in the Polymer's experience? Is it vibrational only?
No, so this depends on the time scale of that motion. So if you want to see vibrational motions, those are fast motions generally. So vibrations will be sub-picosecond time scales. So you would use a time of flight instrument for that. Right, so they're big. When something's moving fast in a vibrational mode, it has a lot of energy. So if a neutron interacts with it, it gets kicked hard, which means we can tell the difference in timing just clocking the difference in the neutron velocities in the spectrometer. If it's a slow motion, the momentum transfer is very small. It's hard to detect that change in velocity. So you need to use the more delicate techniques like backscattering or spin echo. So this would pick up, yes, you could see picosecond motions with spin echo, but its uniqueness is in the fact that it can see out to hundreds of nanoseconds. And so in that case, it really would be things like, okay, let's put a polymer melt in the spectrometer. And I want to see the relaxation time of the chain relative to the relaxation time of the side chain. So there's the backbone, that's covering flow. The side chains might be covering diffusion, right? So you want to design a battery, go to spin echo. That's where they're doing a lot of this research on, okay, so I want my lithium ions to be very mobile, but I want the battery to be a solid. So I have this backbone matrix that has a low relaxation rate, but I have side chains that interact with water and ions, and they're very mobile. And so you create these parts of your polymer matrix that are very fluid, and so electrodiffusion can happen. And then you still have the solid matrix there that doesn't deform. That kind, like you'd be seeing the differences in those two time scales. Yeah. Other questions? Okay, so data formats. How do you actually get this kind of data out? So we talked about what triple axis is just going to give you single points, right? So if this is your dynamic structure factor, so the formal name, so this is the spectrum you see at a given Q value. So I do the experiment this is color scaled for intensity, and it's a function of Q versus energy transfer. So this would be at a time of flight instrument, and the central line there, you can see at 0 energy transfer is the highest intensity, and then it decays away towards energy transfers. Okay, so you do that energy transfer decay, and the shape of that decay tells you about the relative, which motions are changing, etc. You can interpret that data a number of different ways. You can transform it into just pure intensity. You just look at the central line intensity with some defined width, and you integrate the center line. And as the system becomes more dynamic, the center line intensity will drop because the center line is 0 energy transfer. If more things are moving, the intensity leaves the center and goes to the wings, right? So there's actually a conservation of neutron momentum that you're solving here. So like for chemical engineers, conservation laws, right? It's exactly what you see in this. So you have a conservation of the total number of neutrons that enter the system. Their relative intensity coming out tells you whether the system is static or dynamic. You can see that as a function of, say, temperature. So as your system melts, you see the dynamics increase. You can take this and look at it all as a function of different Q values. And you can fit the relative widths to different Q values, and you can calculate a diffusion coefficient or rotational time constant. You can fit these relative intensities, and you can solve for mean square displacement, making an assumption about diffusional motion, right? So if you assume things are in a harmonic well, just diffuse or vibrating around, I can solve for the average mean square displacement in a system. So I can tell you what's the atomic mean square displacement. This is what spin echo data looks like. This is called the intermediate scattering function. And what you see is it decays from 1 to 0. So your normalized intensity, imagine that this value here reflects your sand signal. So it's telling you what's my structure. All right, I have a structure as a function of Q. And now I just look at that. How long does that structure last as a function of time? So if my different wave vectors are telling me about different structural components, this is telling me how long that particular structural component survives in that system. So if I care about, I don't know, some phase separation happens at a defined time, how long does that survive if it's relevant to our average function? All right. So it seems like we're getting towards done. What's the end time for class? 11:05, which is 5 or 2 minutes ago. So let's just make sure. I think that was it before getting to examples. So if you have any questions about this stuff, you're welcome to come say hi. I'll hang out a second in the hall, but then otherwise, just come say hi. I'm in the office all the time. Yeah, see ya.
Were those last two graphs